Hello everyone. This is the video for the Lewis structure worksheet available to everyone, free in the description. If you didn't watch the topic video or you didn't see the answer sheet, the links will be below in the description. Everything completely free as usual. In this video, I'm just going to be going over the entire sheet step by step, the way I would solve them. If you didn't watch my topic video, I suggest you do. It's a really short video. In that video, we talked about the HONC mnemonic. So I'm just going to write it out because it's going to be really useful to us when going through this video. The HONC mnemonic tells us that hydrogen, I'm just going to write hydrogen, and halogens, HAL, like to form one bond. Oxygen, or O, I'm just going to write oxy, likes to form two bonds. N, or nitrogen, NIT, likes to form three bonds. And C, or carbon, likes to form four bonds. And this will really help us out, point us into the right direction of these Lewis structures. What's important is that you still have your periodic table pulled up, and so that you'll be able to calculate how many valence electrons you have in a structure, and you can check your answer after you use the HONC mnemonic and all other structures available to you. Throughout this worksheet, we'll be looking at a couple patterns with the way molecules are written commonly in organic chemistry. We'll later define them as functional groups, but maybe it's useful to get used to how these molecules are written as condensed structures. So first, we're given these compounds. pH 3. Let's calculate how many valence electrons we have in this molecule. Phosphorus has 5 valence electrons. And hydrogen has 1 electron, but there's 3 of them. And so we total have 5 plus 3, 8 valence electrons. I do think that since we only have 1 phosphorus and 3 hydrogens, I think that phosphorus is going to be in the middle, while hydrogen is going to be all around. We're just going to place them around really nice. Maybe something like this. Okay, and we'll really talk about shapes of Lewis structures in a later video. For now, we're gonna write it like this, okay? And using our HONC mnemonic, this is where it really comes in handy. We said that that hydrogen forms one bond, right, or likes to form one bond, and so we're gonna give it what it likes and give it one bond, okay? And then we're just gonna count how many bonds we have, how many electrons we have written in this structure. Each line is 2 electrons, and so we have 3 lines, which means we have 6 electrons in the structure. However, we need a total of 8. And so what we can do is really just add a lone pair. And by adding a lone pair, make these a little thicker, by adding a lone pair, we have 8 valence electrons in the structure. The next problem, CH3Cl, once again, let's count how many valence electrons we have total. Carbon has 4 valence electrons. Each hydrogen has 1 valence electron. We have 3 of them. And chlorine and halogen has 7 valence electron, which equals out to 4 plus 3 plus 7 for a total of 14 valence electrons. Since we have 3 hydrogens, I don't think that that's going to be our central atom. Carbon versus chlorine, usually carbon ends up being our central atom. And we're just going to surround the rest with our remaining elements. This is where the HONC mnemonic really comes in handy. We said that hydrogen and halogens like to form one bond. Chlorine is a halogen as well as when we have hydrogens. And so let's give it what it wants by forming bonds everywhere. And if we count everything up, we have 4 bonds. Each of them have 2 electrons, which means we have 8. But we need 14. So we need somehow to have 6 electrons left. This is the type of patterns that I'm telling you we're going to see. A lot of the halogens you'll see will have 1 bond and 3 pairs of valence electrons all around. And this added up will form 14 valence electrons, the amount that we need. This is a pattern you're going to see very often with the halogens. You're going to see 1 bond as well as 3 pairs of lone electrons. Br2, dibromine or bromine gas, maybe. I don't even know what the name is. We have 7 valence electrons per bromine, but there's 2 of them. So we have 14 valence electrons in total. We don't really have a central atom because we only have two elements. And so we're probably going to be connected to each other. Again, bromine is a halogen. And so according to our HONC mnemonic, halogens like to form one bond. So we're probably going to have one bond in between each other. And again, the halogens like to form three pairs of lone electrons. And so I think most likely it's going to look like something like this, in which we form, if you count it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14 electrons in this valence electron, into this Lewis structure. So that makes sense. The next problem, HNO2, let's count up the valence electrons. Hydrogen has one valence electron. Nitrogen has 5 valence electrons, and each oxygen has 6 valence electrons for a total of 6 plus 12, 18 valence electrons. Once again, this is where a HONC mnemonic becomes so important. You will not be able, it'll be really hard to draw a Lewis structure without really knowing the patterns that these elements tend to form. And so if let's try to somehow organize this structure to be able to give every element what it wants. Check this out. By drawing it this way, oxygen ends up having 2 bonds, nitrogen ends up having 3 bonds, oxygen, again, ends up having 2 bonds, and hydrogen, once again, ends up having 1 bond. And so we can really organize these structures in any way, and knowing your HONC mnemonic will really point you into the right direction with forming these Lewis structures. Let's count up how many bonds we have at this point. We have 1, 2, 3, 4 bonds. Each one has 2 electrons, which means we have 8 valence electrons in the structure right now. We need to add 10. And so what we're going to do is we're going to fill up the rest. Oxygen tends to have 2 valence electrons, 2 bonds, and 2 pairs of lone electrons. This is just a pattern, once again, that you tend to see. And then nitrogen tends to form 3 bonds and 1 pair of lone electrons. Let me make it, keeps erasing. So something like that. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We add up to 18 valence electrons in this molecule, and so we drew the correct Lewis structure. The next problem, C2H2. Each carbon has 4 valence electrons. We have 2 of them. And each hydrogen has 1 valence electron. So this adds up to, let's see, 8 plus 2, 10 valence electrons total. Once again, we don't have a central atom, obviously, because, well, we have 2 of each. And so let's try to organize this molecule into somehow have the amount of bonds that it wants. And so by doing this, if we give hydrogen 1 bond and fill up the rest for carbon, we end up having the exact amount of bonds that we want. Hydrogen, both of the hydrogens have 1 bond, and both of the carbons have 4 bonds. According to our HONC mnemonic, that works. Let's count up our valence electrons as it is in this molecule. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 valence electrons, and our structure should have 10 valence electrons, which means we are correct. In the next structure, let's move on. We have carbon, 4 valence electrons, 3 hydrogens, 1 nitrogen, and again 2 hydrogens. Together that adds up to 4 plus 3 plus 5 plus 2, that's 7 plus 7, 14 valence electrons. Then once again, let's try to form a structure that really makes sense. This is yet another pattern. Let's not put a bond there yet. Another pattern that you tend to see. Carbon really likes to be surrounded by hydrogens and then connected to other stuff. And so by doing this, we end up giving everything the amount of bonds that it wants. By doing this, each hydrogen only has 1 bond, the carbon over here has 4 bonds, and the nitrogen has 3 bonds. And if you see the pattern, nitrogen will again have just 1 lone pair. And if we count all our valence electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have the correct number of valence electrons. And the next problem, SO4 2-. This should be familiar, actually, this structure. This seems a lot like your strong base, H2SO4. I'm kind of getting ahead of our course, but in Gen Chem, you should have learned this molecule. This is a really strong acid. It's pretty useful, actually. We come back to this in organic chemistry. It becomes important, but I'm just going to kind of erase it. It's not relevant for us right now. Let's count them how many valence electrons it needs. Sulfur has six electrons. Each oxygen has 6 electrons, and so that ends up to 24 plus 6, 30 total. But we do have a -2 charge, and so we kind of have to add 2 to make 32. We have 4 oxygens and 1 sulfur, so I'm putting my bets that sulfur is going to be in the middle of our structure. And if we follow our HONC mnemonic, oxygen wants to have 2 bonds each. And it's also going to form 2 lone pairs. And so let's count up how many valence electrons we actually have in the structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. We have 2 extra valence electrons in this structure. And we also don't have a charge. So this structure is actually incorrect. But if we remove 1 bond and add some valence electrons to these oxygens, we end up with a negative charge. On each of these oxygens. And if we count again, this will add up to 32 valence electrons and a -2 charge. The charge, if you guys aren't really sure about that, we'll go into detail in the next video, formal charges. Again, on my YouTube page, check that out. Also another worksheet for that and an explainer video. Hydrogen cyanide, this is a pretty popular molecule. It's very, very, very poisonous. Hydrogen has 1 valence electron. Carbon has 4 valence electrons. Nitrogen has 5 valence electrons, so this adds up to 10 valence electrons. And to try to organize this molecule to give everything what it wants. And so hydrogen wants 1 bond, while carbon wants 4 bonds. Nitrogen wants 1 bond. And so this side nitrogen ends up having 3 bonds, while carbon has 4 bonds. And everything is exactly the way we want it. We're also going to have a lone pair on nitrogen, as it usually does. Let me undo that. And if we count it up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we have 10 valence electrons in the structure, as the way we should have. Let's do SO2. Sulfur has 6 valence electrons, and we have 2 oxygens. Each also have 6 valence electrons. And so we form 6 plus 12 for a total of 18 valence electrons. I think that, well, we have 2 oxygens, and so I think sulfur is probably going to end up in the middle. Right? Each oxygen wants to have 2 bonds and 2 lone pairs, as it usually does. Let's count up the valence electrons as it is right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We're missing 2 electrons, and so if we add it to the sulfur here, that works out completely. And notice that in the video, the Lewis structure video, I said sulfur 6, SS, kind of an easy way to remember it. 1, 2, 3, 4, 5, 6. We have formed 6 bonds to the sulfur if you count each valence electron, each lone electron as 1. The next problem, CH4. Carbon has 4 valence electrons. We have 4 hydrogens, each with 1 electron. And so we have 8 total valence electrons. I think carbon is probably going to be in the middle, as it usually is, surrounded by hydrogens. And we're going to try to form 1 bond to each hydrogen. That way carbon ends up with 4 bonds, and each hydrogen ends up with 1 bond. And if we count up, we have 1, 2, 3, 4, 5, 6, 7, 8 total valence electrons. which is exactly what we need in this molecule. And this is actually the same example we had in the video of the Lewis structures. The next problem, C2H4. Let's count up how many valence electrons we have total. We have 2 carbons, each with 4 valence electrons, and 4 hydrogens, each with 1 valence electron. And we form 8 plus 4 for a total of 12 valence electrons. Let's try to organize everything to give it what it wants. Each hydrogen probably wants 1 bond. And each carbon wants 4 bonds. By giving it a double bond, we end up with 4 bonds on each carbon. And let's count up what we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The structure is correct. We end up with the correct amount of valence electrons total. The next structure, we have 4 for carbons, 2, 1, and then 6 valence electrons in oxygen. We have 4 plus 2 plus 6 for a total of 6 plus 6, 12 valence electrons. Let's try to organize everything with carbon in the center. So hydrogen's probably surrounding it, oxygen also surrounding it. If we try to give hydrogen the amount of bonds it wants and oxygen the amount of bonds it wants, we end up giving everything what it wants. Keep saying what it wants, but really end up falling into place. Each hydrogen wants 1 bond and gets 1 bond. Each oxygen, well, 1 oxygen wants 2 bonds and gets 1 bond. And carbon always wants 4 bonds and it ends up with 4 bonds. However, oxygen usually also has 2 lone pairs on it. Let's count up what we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is the correct structure, the amount of valence electrons we need. The next problem, carbon has 4 valence electrons. Chlorine has 7 valence electrons. And so what we end up having is 4 plus 28, which equals to 32 total. I think carbon is probably going to be in the center, and chlorines are going to surround it. And so we're going to have 1 bond. Try to give 1 bond to each chlorine. Why? Because halogens, chlorine is a halogen, likes to form 1 bond. However, halogens also have 3 lone pairs. Per they also like 3 lone pairs as well as a bond. So let's count this up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. If you count this up, it does add up to 32. Just take my word for it. The next problem, carbon likes to form 4 bonds. Oxygen likes to form 6, or it has 4 valence electrons. I don't know why I said 4 bonds. It has 4 valence electrons. Carbon has 6 valence electrons for a total of 18, right? No, 12 plus 4, 16. Can't do math. And so let's try to have carbon in the center with oxygen surrounding it. If we give oxygen what it wants, 2 bonds, we also end up getting carbon what it wants with 4 bonds. Oxygen usually also has these 2 lone pairs around it. And if we count everything up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is the correct amount of valence electrons, exactly what we need. The next problem, C2H5. Let's count it up. 2 times 4 plus 5 times 1 plus 6 plus 1. So we end up having 8 plus 5 plus 6 plus 1. So 13 plus 7, 20 valence electrons. Let's try to organize everything to give it exactly what it wants. Usually, carbons like to be surrounded by hydrogens. This is a pretty tricky example, but this is useful to get used to, because usually these structures will be written exactly as they are. And so if you see OH, it probably is actually OH, right? Oxygen connected to hydrogen. And we will talk about what this actually is in a future video. These are functional groups. Molecules tend to look a certain way, like there's a pattern that they look like. And so you'll see this very often. Oxygen also tends to have
two lone pairs around it, as well as 2 bonds. So if we count everything up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, we have the correct number of valence electrons. In the next problem, something similar, we have 2 times 4 plus 5 times 1 plus 7, so 8 plus 5 plus 7, so we have 13 plus 7, again for a total of 20 valence electrons. Let's try to organize everything how it wants to be. So H, C, H, running out of space over here, Cl, it's probably going to look like that because it's a halogen. So if we count everything up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 20 valence electrons in the structure, which means we are correct. In this next problem, let's count up our valence electrons. We're just going to group these carbons together. So you have 2 carbons. We have a total of 6 hydrogens and 1 oxygen, which means we have 8 plus 6 plus 6. So that's 8 plus 12 for a total of 20. The condensed formulas, these are condensed formulas, they really tell us exactly how we need to draw them. It's kind of like a little cheat code. Probably going to have oxygen in the middle and carbon surrounded by hydrogens. Notice that we literally drew this the exact same way as they wrote it for us. And if we try to give everything the number of bonds it wants and the number of lone pairs that everything wants, as we've talked about a couple times in this video, we end up forming exactly what we need. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. For a total of 20 valence electrons in this Lewis structure. The next problem, this is kind of advanced, but this little part, COOH, is also a pattern that we'll learn and define. But we have a total of 2 carbons. Oops. Yeah, erase this. We have 2 carbons, a total of 4 hydrogens, and 2 oxygens. Oops. So a total of 8 plus 4 plus 12. So we have 12 plus 12, 24 total valence electrons. Let's try to draw it exactly as they told us. Notice that this is literally exactly what they told us. We're just drawing it very literally. And if that ends up working out, it does, right? Everything in this molecule ends up with the exact amount of bonds that it wants. And if we try to count this up, let's give oxygen the amount of lone pairs it wants as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 24 valence electrons, the exact number of valence electrons that we need. The last 3 problems, let's get these done. We have 3 carbons. Oops. 3 carbons. Each has 4 valence electrons. And then 8 hydrogens. For a total of 12 plus 8, 20 valence electrons. Oops. And so let's try to figure out how we can draw this. Let's try to put all the carbons in the center and the hydrogens surrounding them. And this way, we end up, if we form one bond to each of the hydrogens, we end up with 4 bonds in each of the carbons, and if we counted it up, we would end up with 20 valence electrons, which means our Lewis structure is correct. Second to last problem, we have 1 carbon, 1 oxygen, and 2 hydrogens, which add up to 10 plus 2, 12 total valence electrons. And so if we tried to put this in the center, we already did this problem before. I didn't notice that I put a duplicate. But it would end up looking like this. Oh, this is the same thing as well. Notice that no matter how they wrote it for us, it's literally the same thing, right? And so we really can change these formulas the way they write them for us, but our Lewis structure does not change. So that's a really, really interesting thing that you should maybe keep in mind. The next part of this, what I'm asking in this picture, in this next question, is really your HONC mnemonic, right? Ideally make. So something like this. Let's write it out again. Carbon would ideally form 4 bonds. Oxygen would ideally form 2 bonds. Nitrogen ideally forms 3 bonds. Hydrogen ideally forms 1 bond. And fluorine, chlorine, bromine, iodine, these are all your halogens. And so they all ideally form also 1 bond. The next couple problems, which of the following is the Lewis structure for CH3, CH2, O2H? Notice that we're probably going to write this out the exact way that they wrote it for us, right? Literally, like it's very literal, right? The Lewis structure looks very similar to how our molecule looks like. And so try to draw 2 O's maybe, and something like this. If we end up doing that, we give everything the exact amount of bonds that it wants. And count up your valence electrons, it would work. And so what our answer is A. Which of the following does the central atom have 2 pairs of non-bonding electrons? The only way to really do this is to draw your Lewis structure. There's no other way to do this. And so if we try to draw ozone or O3, you don't really have to know the name. But what we end up forming is something like this. And Lewis structure would look something like this, with a positive charge here. And this is our central atom. It does not have 2 pairs of non-bonding electrons. It only has 1 pair of non-bonding electrons. CO2, carbon dioxide, the Lewis structure ends up looking like this. Carbon, our central atom, does not have any lone non-bonding electrons at all. So definitely not. CO3. Maybe something like this. If we give it this, we end up with 2 extra valence electrons, if you counted it up. And carbon, once again, our central atom has no non-bonding electrons. NH4 plus probably looks something like this. 1 single bond to each hydrogen. This would end up with 1 less electron than what we were supposed to get, forming a positive charge. And so this has no valence electrons. However, if we drew something like this, H2S, we would end up with 2 non-bonding electrons, which means H2S is the correct answer. The next problem, which is not a correct Lewis structure, let's refer to our little mnemonic to maybe check. Maybe if one of these elements has an incorrect number of bonds, and there's no charge present, then maybe the Lewis structure is incorrect. Let's go one by one. H has 1 bond, good. H has 1 bond, good. Nitrogen has 3 bonds, good. However, fluorine has 2 bonds. Halogens are supposed to have 1 bond. And so this is, hey, let's add an arrow mark. Maybe this is our wrong answer. Hydrogen in each of these has 1 bond. Carbon has 4 bonds. Fluorine has 1 bond. Everything is the way it's supposed to be. So this is correct. Oxygen has 2 bonds. Oxygen has 2 bonds. Hydrogen has 1 bond. Hydrogen has 1 bond. So this is a correct structure. Oxygen has 2 bonds. Hydrogen has 1 bond. Oxygen has 2 bonds. Hydrogen has 1 bond. And again, oxygen has 1 bond. Hydrogen has 1 bond. And so boron actually likes to form 3 bonds. This is something we talk about later. And so this is also a correct structure. And our incorrect Lewis structure is A. What is the correct Lewis structure for CH3CO2H? We actually did this before, I think, in one of the previous problems. Let's draw this out. Very literal. The exact way that they wrote it for us, we're going to draw it out. COOH. I think we ended up with this structure before. If you count up the valence electrons, this would work. And so the correct answer is D. Which of these compounds possess a single unpaired electrons? Again, like the previous problem, similar to this, we really just have to draw the Lewis structure to figure this out. So nitrogen wants 2 bonds. And so both of them have a lone pair, which is not a single unpaired electron. Oxygen is our central atom here. We have nitrogen all around it, maybe something like this. And so it would look like something like this. N2O, our next structure, if we try to organize it in a way to give everything the way it wants, it would end up looking like so. If we gave it maybe 3 of these and 1 bond here, we end up with the correct number of valence electrons. However, none of these have a single unpaired electron, so B is incorrect. Let's look at NO. If we gave 2 bonds, try to have 2 bonds here, we had something like this, we would actually end up with a extra lone pair over here, or an extra lone electron. And so our valence structure, our Lewis structure, would really end up looking like this. Let me make these a little darker. And this ends up being our Lewis structure with a single unpaired electron. This concludes all of the questions in the Lewis structure worksheet. All of these worksheets are available in the description. Check them out. Everything is completely free. If you're very questionable on this topic, go back to the video linked below in the description as well, and at the end of this video, and check out, maybe it's just a 2-minute, 3-minute video. Check out that video to maybe recall all the information that you need to answer this worksheet. And I'll see you guys in the next one.